maybe we give it a couple of more minutes and then we can start.
Absolutely, anytime.
Trying to collect a few things. Okay, so let's get started. Today we're happy to have Dalimil give us a talk on sharp boundaries for the Swampland. Please go ahead.
Okay, thanks very much, Ibu, for the introduction. And I would, of course, like to start by thanking the organizers for inviting me to give this talk. And also, I would like to encourage you to ask questions at any point during the talk, and any questions are welcome. I'll try to monitor the chat window, so you can also feel free to ask there. This talk will be based on a paper that came out recently in collaboration with some fantastic people, Simon Karen-Ott, Leonardo Rastelli, and David Simons-Daffin. And the title is Sharp Boundaries for the Swampland. Whoops, okay. Sorry, just some technical issues with my chair. All right, so the sort of the grand goal here is to put some constraints on theories of quantum gravity. So let me start by stating some grand questions, all of which motivated this work, but none of which I'll really come close to answering in this talk. So there's a sort of obvious experimental observation, which is that our universe contains gravity. So obviously we'd like to learn as much as possible about gravity and constrain possible theories of gravity or possible universes. So we can ask, what is the set of universes which contain gravity, which are compatible with some fundamental physical principles? And of course, this is a very loaded question. I didn't tell you what the fundamental principles are, and okay, so this is just like the very broad question that I'll try to say something maybe new about. In particular, we still have relatively little idea whether there are only very few options or a vast landscape of possibilities for fundamental laws of physics which contain gravity. Closely related to that is the question whether all theories of quantum gravity necessarily come from string theory, or whether there are some sort of islands completely disconnected from the world of string theory. Another related question is, how does the answer to all of these questions depend on the space-time asymptotics? So for example, you can imagine imposing that the universe is asymptotics of ADS, flat space, or the Sitter space. Of course, the last option being the most physically relevant. In the first case, we have a relatively precise definition of what it means to have a theory of quantum gravity in the Sitter space. And in the second case, relatively slightly less. And in the last case, we know really quite little about what it would mean. And yeah, in this talk, I'm going to mostly focus on flat space, but there's also an interesting work in progress in the context of anti-de Sitter space. And finally, so the question which I'll really focus on today is the question: which low energy effective field theories admit a UV completion? So some of this is maybe the most experimentally important question, because currently with our current experiments we can't really probe the Planck scale. So the question which sort of makes sense to ask is what are the constraints of UV completeness on the low energy physics? And that's of course a question that's been worked on by many people in the audience and others. So hopefully I'll manage to say something new about it. So as I said, in this talk, I'll focus on this last question in the context of flat space. But perhaps if there's time at the end, I can also say a little bit about this work in progress on ADS. All right, so which effective field theories admit a UV completion? As I said, this is a old question with lots of interesting work that's been done on it. For example, in the context of this is really the heart of the so-called Swampland program. And by now, it's clear that there are powerful constraints on IR coming from UV consistencies. So that not every effective field theory that you can write down at low energies necessarily admits a UV completion. For example, it has been argued that a consistent UV complete theory of quantum gravity should have no global symmetries, so that eventually all global symmetries will be broken by sufficiently high energy operators, or they'll be gauged. Other examples of such Swampland criteria are the weak gravity conjecture, distant conjecture, and many others, which sort of form a beautiful, intricate web of related conjectures or results. Now, the results so far have some drawbacks, although they're wonderful. They still have several drawbacks. So one is that they are often conjectural and typically based on examples. So they're sort of based on looking at various compactifications of string theory and seeing what happens in those examples and extrapolating from that. That's not always true, but in many cases that's the case. Another drawback is that many of the arguments, like when, for example, we want to compare two quantities, these arguments would only lead to parametric bounds, that you'd be able to say that one quantity must be much smaller than another quantity. What one would prefer, ideally, if you want to really precisely constrain quantum gravity, is to have some rigorous bootstrap type arguments based on completely general physical principles. So that's the first point that one would like to improve. Another point is to replace the parametric bounds by precise bounds. If we have two quantities, we'd like to be able to put a precise bound on this order 1 coefficient, which sits in some kind of inequality. And I will discuss some concrete examples in the rest of the talk. So something like what I have in mind is something what happened in the context of conformal field theories of low central charge. This is the success story of the conformal bootstrap. In that case, we know very precisely what these general principles are. They are just the constraints of the conformal bootstrap, so crossing symmetry and maybe modular invariance in 2 dimensions and so on. And these constraints seem to be sufficient to actually corner individual theories. So here's a famous plot taken from a paper by Kospol and Simons, Duffin, and Vicky, which shows the island inside of which the 3D Ising model lies. So there's, there are some precise non-parametric bounds that if you're outside of the island, this is disallowed. If you're inside, it's allowed. And there's a very interesting theory which basically saturates the bound. And so somehow the ambition is to have a similar program that can produce precise sharp bounds in the parameter space of quantum gravity theories, and hope that some interesting theories actually saturate these bounds. So one would like to sort of figure out what is this right parameter space and what are the constraints, and maybe find a set of islands. Okay, so that's the ambition. Of course, one possibility is to literally use conformal bootstrap in the context of ADS-CFT. So there's some noise in the background. I don't know if there's some going on. Okay, yeah, that's better. Yeah, so one possibility would be just to use ADS-CFT and constrain quantum gravity using the conformal bootstrap, and that's proving a little tricky. Essentially because the conformal bootstrap works very well for low central charge theories and not so well for high central charge theories, but that's not really going to be the main subject of the talk, because in this talk I'll focus on quantum gravity in flat space. Okay, so here's the roadmap for the rest of the talk. I basically need to explain 3 things. The first thing that I need to explain is what is the space of the a priori parameter. So what is this? What are the axes in this picture? And these parameters will just be the irrelevant couplings in the low energy effective field theory of gravity, maybe coupled to some other fields. So that's point number 1. The second point that I will try to explain is what are the fundamental principles and assumptions that I'll use to constrain these parameters. And those principles will be just causality and unitarity manifested in some mathematical properties of the 2-to-2 scattering S matrix. And finally, I will need to explain how do we use these principles to put bound on the parameters. And the way that I'll do this is to use dispersion relations for the S matrix in some novel way. So I'll make that precise as we go on. Okay, so are there any questions before I move on? Okay.
Actually, I have a question. So is crossing not going to be one of your principles?
It's going to be, yeah, it's going to be one of the principles, but in some sense it's an obvious, somewhat of an, well, okay, you can say it's a little tricky. So I will assume that the particles that we scatter are identical, so there is some crossing symmetry, and
Okay.
in some sense crossing symmetry is a bit subtle, relates to analytic continuation of the S matrix, and it's related to causality. So really, crossing is a consequence of causality.
Okay.
Thanks for the question. Any others? All right, so let me begin by explaining more about this. So here is, let me say a few words about what we expect the low energy effective field theory of gravity to look like. Now, I should say this part is motivational. I will, eventually the actual results that I'll present will be in a context of a more of a toy model with a scalar field, but I want to begin by sort of explaining what one eventually wants to do, and that relates to the gravitation, to the action for pure gravity. So the action for gravity at low energy looks like this. There's a G Newton down here, which just controls the strength of the gravitational interaction. Then there's the Einstein-Hilbert term, supplemented by corrections. Now, all of these interactions are irrelevant because the coupling has negative dimension. It can be written in terms of the Planck scale like this. So this is some negative power in dimension greater than 2. And I also decided to put the sort of to extract the overall coupling outside, so that well, it's gonna be a more useful convention. So this effective field theory supposed to work for some energies which are much below the UV cutoff, and this UV cutoff, capital M, is presumably below the Planck scale. So what this means is that, well, certainly this effective field theory doesn't work all the way up to the Planck scale, and typically we expect, for example, like in weakly coupled string theory, that there are some additional particles which come in at energies below the Planck scale, and this energy where new particles appear will be called capital M. The expectation from general effective field theory arguments is that these coefficients alpha 2 and alpha 3 and all the higher ones should be suppressed by inverse powers of this UV cutoff M. So in particular, alpha 2 has dimensions of negative energy squared, and alpha 3 has dimensions m to the minus 4. So we expect that they scale like this with some order 1 numbers in a general gravitational theory. And it was actually argued using causality in this beautiful paper that if they are not suppressed like this, there is some problem. But this paper didn't give precise bounds on these order 1 coefficients. So there is a natural task, which is to prove rigorous bounds on these order 1 coefficients. So we would like to rigorously prove that the absolute value of alpha 2 is bounded by some order 1 coefficient times m to the minus 2, and similar for alpha 3 and the corresponding power coming from dimensional analysis. And this is not just some academic question. You could actually imagine being able to measure these coefficients alpha 2 and alpha 3 by looking at inflationary correlators. So if the Hubble scale during inflation reaches all the way up to the value of this UV cutoff, then you'll be able to probe these coefficients, and some bounds can then be compared directly to experiment hypothetically. Okay, so that's that's what one would like to do. And now let me explain why one should sort of first focus on weakly coupled theories. So here I'm just reproducing the action that I wrote before, the gravity action. And the natural scale for the UV cutoff will be the Planck scale. So one may hope to be able to prove that in all consistent theories, this alpha 2 is much less than some inverse power of the Planck scale times some order 1 number. But this is actually too ambitious because there is a simple counterexample, namely weakly coupled string theory. So let's imagine that we have some string theory where G string is much less than 1. Then the spectrum looks like this. So at low energies, we have just the massless fields, such as the gravitons. Then there is a string scale, which is in this case the same as the UV cutoff. The string scale is parametrically suppressed compared to the Planck scale by some positive power of G string. And then eventually there's the Planck scale where there could be all sorts of objects such as black holes, and who knows what happens at the Planck scale. And the important point is that in this regime where G string is much smaller than 1, the alpha 2 is not suppressed by the inverse power of Planck scale, but actually by inverse power of this scale M, of the string scale. And this scale is much bigger. This value is much bigger than the inverse power of the Planck scale. So we'll never succeed at showing that in all examples alpha 2 is suppressed by parts of the Planck scale. But what we can do, what we can hope for, this is the natural first goal, is to prove bounds in the case when the coupling is weak, bounds in terms of the UV cutoff. So not in terms of the Planck scale, but in terms of the UV cutoff, like this. And this bound is certainly satisfied also in weakly coupled string theory. Indeed, the alpha 2 will, well, alpha actually in type 2 alpha 2 is 0, but I guess in heterotic it's not. So maybe that's alpha 3. Well, so certainly this bound is satisfied also in weakly coupled string theory, and one would like to rigorously prove that such a bound is always correct. Okay, maybe there are some questions.
Does something special happen when the bound is precisely saturated?
Yeah, that'd be great. If first of all, we haven't really found an example where the bound is saturated by string theory. But if it were true, then for example, by analogy with what is possible in a conformal bootstrap, one would be able to extract a lot of non-trivial information about the theory. So, for instance, because the 3D Ising model saturates some bounds coming from the conformal bootstrap, you can actually use this to extract the spectrum of many operators. So you could hope that something like this would happen here too. And I'm going to show an example of a precise bound later, and a sort of interesting theory which saturates it, but that theory looks nothing like string theory. So we are a bit puzzled by that. We are not really sure whether that can be a physics. Well, I'll get to it. I'll get to it later. Thanks for the question. Okay, so in this context of weak coupling, one can ignore loop effects at a scale m and below, and this is a nice simplifying assumption that will help us later on, but it's not really so important. So maybe later I'll comment on how one could imagine incorporating loops into this program. Okay, yeah, so before I go on, let me just make a side comment about universality of string theory. So sort of a generalization of this idea of bounding the irrelevant couplings in the action is to try to classify all weakly coupled theories of gravity. So you use all possible constraints and see what these parameters should be. And in fact, currently we only have 3 examples. Well, 3 examples of such consistent theories in flat space, namely the S matrix of Einstein gravity, the heterotic string S matrix, and the type 2 string. So this is all at tree level. There could be, so basically the idea is that the compactification doesn't really matter at tree level. If you only scatter gravitons at tree level, all of these well, all the internal manifolds are going to give you the same scattering amplitudes at tree level. But this is a point which has been emphasized many times over the last couple of years by Nima, and there have also been some interesting papers by a group in India. One can wonder whether this is a complete list, whether there are some additional theories of gravity that we have missed. In fact, there is also a related question in the absence of gravity, which is to try to classify all theories of weakly coupled massive higher spin particles. So the special thing that happens with gravity is that there is a massless spin 2 particle, but you can imagine having a theory of infinitely many interacting massive higher spin particles. Try to classify what such theories are, and we believe that there are many examples of such theories, namely all asymptotically free gauge theories at large n would give you such examples. So there, because of confinement, you got infinite towers of massive higher spin particles, and when n color is large, all of these particles are weakly interacting. There was an interesting paper in 2014 which studied such theories purely from the bootstrap from the S matrix bootstrap point of view. Okay, so this was just a side comment where such analysis might eventually go to. Okay, so why are theories of gravity constrained? Was there a question? Okay, yeah. Let me give a physical argument now. Following the second paper by Kamanho, Edelstein, Maldacen, and Zhiboedov, why weakly coupled theories of gravity are constrained due to causality. The basic physical idea is that when the subleading irrelevant interactions are too large, then they can lead to superluminal propagation. So now I'm reviewing the thought experiment of this second paper. The thought experiment is the following: you can consider some particle which is propagating at a very high speed, some highly energetic particle, and this particle creates a shock wave. So it back reacts on the geometry, and it creates a shock wave in the space-time. And then we have a second particle, that's the blue line over here, which propagates through this background, through the shock wave. And because of the presence of this non-trivial back-reacted metric, there is some shift. So the particle starts here, then it hits the shock wave, and then there is some shift along this null direction until it keeps propagating further. And this shift depends on several things. So first of all, I'm only drawing here a two-dimensional picture, but really the picture has some transverse directions. And the blue particle is assumed to be separated from this red particle by some impact parameter B in the transverse direction. So B here is the transverse impact parameter. And so one can compute what this shift should be, and it would be inconsistent if we found that this shift delta x minus is negative, because that would mean that this particle basically traveled back in time. You could violate causality using such a thought experiment, and this shift can be calculated starting from the action, with the Einstein-Hilbert term and the alpha 2 and alpha 3 corrections, and it looks like this. So the first term, one, just is the answer in the Einstein-Hilbert, just using the Einstein-Hilbert term, and we see it's positive. So G Newton is positive. Energy is also the energy of the E is the energy of this red particle. So we see that the answer is positive, as it should be. So if we only have pure Einstein gravity, there's actually a time delay. So gravity always slows you down. But the additional corrections like alpha 2 and alpha 3 can lead to either a time shift, time delay, or a time advance, depending on the polarization of the graviton that we are scattering, the blue particle. So if we look at this this formula at sufficiently small b, so sufficiently small impact parameter, then the second and third term can dominate. So first maybe for some fixed alpha 2 and alpha 3, when you make b sufficiently small, the last term is going to dominate, and it will lead to a time advance. So it will be inconsistent. So this basically means that there should be some upper bound on the, so there should be some lower bound on b, beyond which we cannot really consider this, and that's precisely where the UV cutoff comes in. So as I already said, superluminal propagation occurs unless there is an upper bound on the absolute values of this alpha 2 and alpha 3 in terms of the minimal impact parameter where this calculation makes sense. And this calculation makes sense when b is greater than the UV cutoff of the theory. If you make it smaller, then there are new particles that the low IREFT doesn't know about that you should really take into account. So this is the physical argument, but it's kind of hard to turn this physical argument into precise bounds on alpha 2 and alpha 3. So we only, you can use it to argue that alpha 2 and alpha 3 are parametrically suppressed by some inverse powers of m, but they don't really tell you what these order 1 coefficients are. So one would hope to replace these parametric bounds by the sharp bound. So eventually, the eventual goal in the context of this problem would be to produce a plot in the two-dimensional space of alpha 2 times m squared, this is some dimensionless number, and alpha 3 times m to the 4, another dimensionless number, where you have some compact region, which is theoretically allowed, and such that everything outside is disallowed. So such a plot should exist given our current knowledge, and the technical goal is to actually produce such a plot. And this argument unfortunately doesn't seem to, well, it'll be fantastic to make this physical argument so precise that you can produce such a plot, but that's not really the route that I'll take in the rest of the talk. Are there any questions about the slide or anything that I've explained so far?
Is it obvious the blob should be simply connected?
I think probably yeah. If you only, well, it depends what exactly you impose, but if you only impose 2 to 2, so this thought experiment was, you can interpret in terms of the 2 to 2 scattering of gravitons. And in that case, I think any convex, if you have 2 solutions of the constraints, then any convex linear combination will also be a solution. And any convex region is simply connected, so then it would follow. But perhaps if we impose some additional constraints, like 2 to n scattering and so on, then anything can happen. I think perhaps. Well, yeah, I think that's right. But in this case, in the simple analysis with 2 to 2 scattering, you will necessarily find something that's convex. All right. So let me now just sketch what our main result is. The result is in the context not just of pure gravity, but of gravity together with a light scalar field. So that's a simplification because it allows us to simply scatter the scalar particle, and the sort of the group theory that is much simpler because we don't have to deal with external polarizations. But surprisingly, also in this case, one can find bounds in the presence of gravity. So here is what the most general action for such a theory is. There's again the Einstein-Hilbert term for gravity. Well, okay, I'm only keeping terms which will be important, which will contribute to tree-level 2 to 2 scattering of the scalar field phi. Okay, so the scalar field phi can exchange the graviton, so that's why I should keep the kinetic term for the graviton. There's a kinetic term for the phi field, and then there's an infinite tower of quartic interactions for the phi field. So there is of course the phi to the 4 interaction. Yeah, I suppose I'm also assuming that there's a Z2 symmetry acting on phi as phi goes to minus phi, but that's not really crucial. It just simplifies the action a bit. So there is this quartic term and an infinite tower of higher derivative quartic terms. So this, for example, there is this famous coupling, which is like the partial phi to the 4 term. which has been analyzed by in many papers and is known to be non-negative in non-gravitational theories. So this is the partial phi to the 4 term, and there's a 6th derivative term, and so on. And the claim is that using equations of motion and integration by parts, you can reduce any action of massless scalar phi and gravity to this form, at least if you only keep terms that contribute to the 2-to-2 scattering of phi at tree level. Okay, so what we did is that we considered such a theory, assuming that the UV cutoff is exactly at the value m, and later on I will tell you what exactly that means. Like, this is a subtle point to really explain what it means that the cutoff is at m and not at some number, some order 1 number times m. We also assume that the theory is weakly coupled, so that the UV cutoff is much smaller than the Planck scale. And in that case, we find such a bound on beta 2 and beta 3. So beta 2 is a number of dimension -2. Beta 3 is dimension -4, just by counting the dimension out of these couplings. And as I mentioned, in non-gravitational theories, beta 2 is known to be positive. Here's the plot that we find in dimensions from 5 to 12. Everything to the left of these curves is excluded, and everything to the right is allowed. So, for example, if you focus on the d equals phi case, is this curve. So everything to the left is excluded. So in particular, there's a lower bound on the value of beta 2. Now this lower bound is negative. And there's a pretty simple intuition for that. As I already said, in the absence of gravity, the lower bound on beta 2 would simply be 0. And also, as I mentioned before, gravity can only slow you down. So the fact that gravity slows you down can be compensated by a slightly negative value of beta 2. But there is still a lower bound on the value of beta 2. Just now it's negative. And for any fixed value of beta 2, there's a two-sided bound on the 6th derivative coupling beta 3. All right, so the rest of the talk will be about explaining how we set up the problem and how we arrived at this picture. And I'll also say something a little bit more about the theory that we find at this tip. All right, so what are the fundamental principles and assumptions that go into the analysis? We considered the 2-to-2 scattering of the scalar field phi. So let me denote it by A, S of t. S and t are the usual Mandelstam variables. This is some genuinely Lorentzian observable, just the S matrix, and this is what it looks like. So let's consider this function as a function of complex variable s at some fixed value of u. So s plus t plus u is 0 because we are scattering a massless particle. So if we fix u and vary s, that means we also vary t. This is the structure of singularities in the complex plane in the weakly coupled regime. So first of all, there are some, well, there's a pole at the origin, which comes from the exchange of the graviton, and then there are the cuts, the UV cuts. First, there is the S-channel cut, so corresponding to the exchange of on-shell S-channel particles, and the T-channel cut, just corresponding to T-channel exchanges. I could, if I wasn't assuming that sorry, as I'm working at tree level, there would also be some additional, there could be some additional cuts stretching in this low energy region. But at the leading order, so at tree level, there is literally just the pole at the origin. But in principle, these additional corrections can be taken into account, and maybe if there are some questions, I can say more about it later. Okay, so here are the assumptions. First assumption is causality, and that's physically manifested by analyticity of the S matrix in the complex S plane. So basically, I'll be assuming that this function is holomorphic everywhere away from the singularities shown in this picture. The second assumption is one I've discussed quite extensively already. It's this assumption of weak coupling of the low energy theory. And this assumption dictates a specific form of the expansion of this function around the origin. So suppose we take S to be very small, or both S and T to be very small, then the expansion looks as follows. There are these three terms which just correspond to the graviton exchange in the S, T, and U channel. Then beta 0 is just the phi to the 4 contact interaction with no derivatives. And then there is an infinite tower of polynomial type terms. Beta 2 and beta 3 are the ones that I'll focus on. The beta 2 is the 4 derivative one, so it comes with S squared plus T squared plus U squared. And beta 3 is the 6 derivative one, which corresponds to ST and U. And these are the only 4 and 6 derivative crossing symmetric terms that you can write down. But in principle, I mean, and in general, there's a whole infinite tower of interactions. The weak coupling for me just means that I'm putting the G Newton out in front, so that all the not just the gravitational coupling, but also these derivative couplings are suppressed by the same they're all of the same order. Basically, that's why I'm putting the 8 pi G Newton not just in front of the graviton exchange, but also in front of the higher derivative terms. So in this convention, G Newton expansion in G Newton is literally expansion in loops. Okay, so that was the second assumption. Third assumption is unitarity. And unitarity can be expressed as a constraint on the imaginary part of the S matrix. So here the S matrix develops some cut corresponding to exchange of heavy particles, or contribution of heavy particles to the scattering process. And essentially using the optical theorem tells you that the imaginary part, the optical theorem is a special case of the statement that this imaginary part here can be expanded in Legendre polynomials with positive coefficients. So the way you derive it is that you insert a complete set of states into the 4-point function, or into the overlap between the in and out states. And if you use a complete set of states which diagonalize angular momentum, you will find such an expansion, and the imaginary part must be positive. So the imaginary part of this coefficient must be positive. And finally, maybe the most mysterious condition that will be important is a bound on Regge growth. And this bound says we will require that when we consider the amplitude divided by S squared, then this goes to 0 as we take S to infinity in any complex direction. So here here we are keeping, again, U or T fixed, doesn't matter because everything is crossing symmetric. We are taking S to infinity and assuming that the amplitude goes to 0, essentially goes to 0 faster than S squared. Okay, so now the next slide will be devoted to a further explanation of this fourth condition, but maybe if there are some questions about any of the other three or even all 4 of them, now would be a good time to ask. All right, so why do we believe that this condition is correct? Well, there are essentially 3 ways, 3 possible arguments. One is to simply say that this condition is satisfied in string theory. So in string theory, this is the behavior in the Regge limit. So again, remember we are keeping Q fixed. Also, U is negative in the physical region. So I should say that all of U will always be negative. And in string theory, this is the high energy behavior. It's S to the 2 plus alpha prime U. And because U is negative, this power is always less than 2, meaning that indeed this ratio goes to 0 as goes to infinity. And the reason the ratio behavior looks like this is that there is not just the graviton, but there's a whole Regge trajectory of higher spin massive particles which complement the graviton. So if you only had Einstein gravity, this bound would be violated. So empirical pure Einstein gravity, just the exchange of gravitons, violates our assumptions, and that's somehow how we are imposing that there is some non-trivial UV completion. And that UV completion could be string theory, or it could be something maybe more complicated. All right, so this bound is satisfied in weakly coupled string theory. Another way you could motivate this is using chaos bound type arguments. So there is this classical Regge growth conjecture, which was first argued for in the same wonderful paper that I already mentioned before. And this conjecture simply says that the amplitude is bounded by s squared. So somehow things cannot grow faster than in gravity. And the only way that you can saturate this growth is if you actually have gravity. So in the context of 2-to-2 scattering, this was discussed in this paper, and then it's essentially a special case of the bound on chaos. And finally, there was also a very nice paper this year which discussed this classical Regge growth conjecture. But I would like to stress that this is not really enough for us, because because we really need something slightly stronger, that this ratio goes to 0, not just that it goes to some finite constant. So we need a little more. And to me, the most convincing argument why this is true in theories of gravity is that it's rigorously provable, not in flat space, but in ADS. So in the context of ADS CFT, in the context of scattering in ADS, you can model, you can literally think of the scattering amplitude as a 4-point function in the boundary CFT. And in that case, the relevant regime is the so-called Regge regime of the 4-point function, which is the 4-point function analytically continued to the second sheet. And there is a perfectly rigorous argument, first spelled out by Simon in his Analyticity in Spin paper in 2017, that unitarity and the OPE implies that this 4-point function on the second sheet is bounded by the 4-point function on the first sheet, so in the Euclidean regime. And this non-perturbative bound essentially amounts to improving this exponent from 2 to 1. So really things are bounded by spin 1 non-perturbatively when you go to sufficiently high energy in ADS. There is no corresponding proof in flat space. It would be nice to understand it a little more, maybe using some kind of flat space limit of ADS type arguments. But for now, for the rest of the talk, this will just be an assumption that this is true. All right, so now that I told you what the parameters are and what the principle, what the assumptions are, let me say how to actually get some leverage using dispersion relations. So what are dispersion relations? Dispersion relations are a concrete, quantitative manifestation of the fact that IR and UV are not really decoupled. They need to talk to each other because of causality. And the starting point is just the statement that the integral of a holomorphic function around some closed cycle, not including any singularities, is 0. So we can apply this to the S matrix. So here is the S matrix. If we, well, from causality, it follows that it should be analytic in the upper half plane. So we can integrate it against some function which is itself holomorphic here, and we must get 0. And now we can take this contour and deform it onto the singularities. So first of all, there will be a contribution from infinity, and this is precisely where we need the bound on the Regge growth. So that if the bound on the Regge growth is satisfied, then we can drop the contour at infinity. So that's the only place where it's needed. And the rest of the contributions are the following. So there are 2 additional contributions. One is the one coming from the IR, that's sensitive to the low energy effective field theory and can extract the couplings. And the second part is the UV part, which is just the discontinuity of the amplitude on the UV cuts. So these two contributions together must give you 0, which is the same thing as saying that the contribution from the IR must equal the contribution from the UV. So this is of course a very old story. I'm just reviewing it for completeness, and because it's a nice argument, but this is certainly not new. And the reason why you get bounds on the effect on the EFT couplings is that the UV contributions are positive. So that was the second assumption in the previous slide, 2 slides ago, that the imaginary part over here is some positive number. And this is some integral of a positive quantity principle, and that gives you some positivity constraints on the IR couplings. Right. So how does that work in practice? Okay, so here is an example of such a sum rule of a sum rule which relates the IR and the UV. So here on the left-hand side, I wrote the contribution of the IR. So maybe let me go to the previous slide. So okay, the left-hand side of all the following equations will be contribution of this small circle, and the right-hand side is the contribution of these cuts. So there is some integral over the spectral density of the UV physics. Okay, so the left-hand side, for some specific choice of the weighting function, will be sensitive to the couplings which grow at least as S squared in the UV. So in particular, there is the graviton pole, there is the 4 derivative coupling, 6 derivative coupling, 8 derivative coupling, and so on. And the dispersion relation relates it to some integral. Okay, so maybe I could. Okay, this angular bracket is a weighted integral of the UV spectral density. So there is okay, I should really write this down, but I don't think I will. It's an integral of the imaginary part of the amplitude, which is positive, against this function. Okay, so you should think of this angular bracket as some positive probability measure defined by the UV physics. But we are completely agnostic to what this measure is, besides it being positive. So that's the only thing that we really need. Okay, so let's think about this sum rule a little bit. By the way, this PJ is just the. Maybe let me explain this fraction a little bit more. So as I said, we are integrating over the heavy contributions, where m is the mass, or the energy of the contributions that we are integrating over. So all the contributions are labeled by their energy and their spin in partial wave decomposition. So this is really a sum over J and an integral over M from the UV cutoff above. UV cutoff and higher. So let's think about this sum rule a little bit. Let's take some limits. So first, you can see that as we dial t to 0, the left-hand side grows. It actually blows up strictly in the t equals 0 limit, and it's large and positive, because in region of physical scattering, t is negative, so -1 over t is positive. And if we take t literally to 0 over here, we simply get we get some positive number. It's like 2m. It's like 1 over m squared, because the forward limit of pj is 1. Okay, there's a question in the chat. Oops. Okay, so it follows from the sum rule that G Newton must be positive. In other words, gravity is attractive. So that's not really new, but it's reassuring that the sum rule is compatible with an obvious experimental fact. Now, the way that these sum rules have been used was mostly in the absence of gravity. So if there is no gravity, the first term is absent. We only have some quantum field theory with polynomial interactions, and then we can literally expand this equation around the forward limit. So if we just take t equal to 0, we get the 2 beta 2, and this is what we get. So that the coupling beta 2 is the average of 1 over m squared, which is certainly positive because 1 over m squared is positive. And same thing for beta 3. And this is of course an old story which started with this paper by these authors, who first argued that beta 2 must be positive. So okay, so beta 2 looks like this. Beta 3 is a little more complicated. It's suppressed by a high power of m. And for example, you can argue using this sum rule that beta 3 is suppressed by beta 2 over the UV cutoff squared. Okay, and after this paper explained how beta 2 is bounded, there was a lot of work, actually kind of an explosion of interest in the last year or so. But all of these, I should emphasize especially the EFT Hedron paper, which really studied this systematically and looked at all the possible couplings and so on. But I should emphasize that all of these works work by expanding around the forward limit. So it really fails in the presence of gravity when there is this -1/t. So yeah, this is a problem. One would like to work in the presence of gravity and isolate the individual couplings, presence of gravity, but we cannot expand around the forward limit when there is gravity. So somehow the main technical advance of our paper is that we were able to get around this problem. So now in the remainder of the talk, I'll try to explain how we got around it. So there are essentially two steps. The first step is because we want to focus on the bounds between gravity, beta 2 and beta 3. We want to first get rid of all the higher couplings, and you can do that using crossing symmetry. Like, yeah, let me not go into the technical details of that. But when you do that, you can essentially use some higher subtraction sum rules to eliminate these higher terms, and this will introduce corrections to the right-hand side. So at the end of the day, the outcome is that there is a sum rule which only contains the gravity exchange, the 4 and 6 derivative coupling, as expressed as some UV average. Okay, so that's a slightly simpler part of the idea, and the most important thing is to realize that in the presence of gravity, one shouldn't use wave packets localized around a forward limit. So in other words, one shouldn't expand around a forward limit, but instead localize around small impact parameter. So you could imagine that what one is doing is that you're sort of integrating this equation against some wave packet in momentum space or in T space, and impact parameter space is the Fourier transform, is the Fourier conjugate space. And expanding around a forward limit is like choosing some very flat distribution in impact parameter space. Like, for example, the delta function at the origin of T space is just a constant in impact parameter space. And this leads to problems in the presence of gravity, because gravity is spread out in impact parameter space. So really what you want to do is that you want to localize, you want to integrate this against some wave packet, which is very, very localized in the impact parameter space. In particular, to get this bounds in order 1 coefficients, it should be localized in a region of size 1 over the UV cutoff. And this requires going far from the forward limit, because T is Fourier conjugate to B. One needs to use the dispersion relation for T all the way up to m squared. And that's also why we needed to isolate these couplings, because otherwise the higher couplings would contaminate the result. So effectively, this idea is like a combination of the work of Adams et al. And of Kamanho et al. In this first work, they use dispersion relations around the forward limit, and the physical argument of the second paper that I reviewed tells you that you should look at small impact parameter space scattering. So essentially, what we did in the paper is that we were able to quantitatively use dispersion relations at small impact parameter, and that's what leads to the kind of bounds that we are interested in. Okay, so now what are the results? Firstly, we checked that this idea of localizing impact parameter space is compatible with the forward limit result. So this is kind of a funny plot, because it's just the same plot twice. The forward limit result is shown in blue, and the small impact parameter result is shown in yellow, and they exactly overlap. Sorry, G's should be betas. I forgot to change that. So that there is some compact region in the beta 2 and beta 3 space in the absence of gravity. So in the absence of gravity, you can use the forward limit and everything matches. But in the presence of gravity, you cannot use the forward limit. You need to use a small impact parameter, and that's where we got the plot that I already showed you. As I said, there's a lower bound on beta 2. And one thing that you can ask is what is the spectrum of the theory at this corner? What is the spectrum of the theory minimizing beta 2? And it looks like this. It's a bit of a funny spectrum because you're kind of inclined to say it's like string theory, but it's kind of the exact opposite of string theory. There are these rigid trajectories in the space of spin and the mass. But in string theory, you would expect that the upper triangle is populated, that the spin is bounded from above by the mass. But in this case, it's the other way around. The mass is bounded from above by the spin. So we are not really sure whether this is a physical theory. Probably it's not, but it will be interesting to at least understand quantitatively what is the S matrix. Like that there has to be some mathematical solution of the problem that we are solving, which minimizes beta 2, and it has this spectrum. So maybe one can try to write it down explicitly. Another thing you can do is you can fix beta 2 and ask where are the bounds on the other couplings, and in that case you find closed regions. So there for any fixed value of beta 2 above this lower bound, all the higher couplings must lie in some compact regions. So this is just example. Different colors correspond to different values of the four derivative coupling. We also looked at the same problem in maximal supergravity. There are some simplifications coming from supersymmetry, and the exchange of the graviton multiplet in that case is this 1 over STU type term, and what you can bound is the first content. So beta 0 corresponds to the R to the 4 term. And using this technique of localizing to small impact parameter, you can show that beta 0 m squared is bounded from above by 3. And again, we don't know what the theory is which saturates it. It's a bound which is satisfied in type 2. I guess in type 2 string theory, this is literally 0. But sorry, it's not 0. In type 2 string theory, it's 2 zeta 3. Which is 2.4, and that is indeed less than 3. It'd be interesting to see if we can understand what the theory that saturates this bound is. There was also a very interesting paper by Andrea, Joao, and Pedro recently, the paper called Where is String Theory, where they didn't look at a problem at weak coupling, but didn't really assume anything about the strength of the coupling, and they were able to prove a lower bound on beta 0 in the units of the Planck scale. So it's a slightly different problem. So if you work in the units of Planck scale, then there is no upper bound, as I said before, because weakly coupled string theory just gives you infinity. But there seems to be a lower bound, and it actually seems to be saturated by strongly coupled string theory, by string theory at some in the middle of the conformal manifold. Okay, so that concludes my talk. I'll just quickly summarize. The main point was that I explained to you how to derive bounds on EFT couplings in consistent weakly coupled theories of gravity. The bounds follow from unitarity and causality as implemented by dispersion relations. Now, this is an old program worked on by many people, and the key new idea in our work was to localize the dispersion relation in the transverse impact parameter space instead of taking the forward limit, because this resolves the difficulties presented by the T-channel graviton pole. So T-channel graviton pole blows up in the forward limit, and if you work in impact parameter space, it does not. I would also like to stress that we only use the weak coupling of the effective field theory and not of the UV physics, because UV physics only enters through these UV contributions, and we only assume that the imaginary part is positive and not that it's small. And this really means that one could imagine incorporating EFT loops into the program. You could sort of just correct the contribution of the low energy physics into the sum rules, and proceed from there. Okay, some few words about future directions. It's clear that this technique generalizes to arbitrary S-matrix elements, so it could lead to a systematic bootstrap program for classifying weakly coupled gravity theories from first principles. Just you could imagine doing like mixed correlators or more general type bounds. For example, the problem that I mentioned with external gravitons. And you could try to hope to prove that string theory is unique, or maybe that or find some new possibilities. This program also makes sense in the absence of gravity, where we could consider as matrices of massive higher spin particles and uses to explore the space of large N-gauge theories. Okay, there's a couple more fascinating questions, more speculative, namely what is the relationship to the recent advances in flat space holography, and physically most relevant, whether some kind of sum rules like this could also be true for the supergravity, but I really don't have anything to say about that at this point. So thanks for your attention.
We can take questions now. Just unmute yourself.
Maybe you said this and I missed this, but how come you don't have d equals 4 in all those?
Oh yeah, that's a very good question. It is the same problem as this notorious IR divergence of the four-dimensional gravitational S matrix. So it's basically the quantitative statement is that the integral like dp over p squared diverges. So it's the same problem that we have IR divergence in gravity. And so more specifically, what happens is that there are these. Okay, where is this? Okay, here. All right, so basically we are integrating this against some wave packets, and we need to impose positivity on the UV physics. The right hands, yeah. And basically the positivity of the action on the UV physics is incompatible with finiteness of the action on gravity, and it's the same statement that the d squared p over p squared that diverges. So yeah, the bounds, yeah, the bounds in 4 dimensions are affected by an IR divergence, which means that there is a bound if you assume an IR cutoff, and this IR cutoff is going to introduce some additional logarithmic term. So instead of you need to assume an IR cutoff, and the bound that you can prove under the assumption of the IR cutoff will explicitly include the logarithm of the IR cutoff times capital M in flat space. You could also try to do the same thing in ADS, where there is a natural IR cutoff, namely the size of the ADS, and in that case, you don't need to assume anything else. You will just find a bound which will have some logarithm of the radius of ADS, or logarithm of the UV scale in the units of radius of ADS. If you wanted to do it rigorously in flat space, you would first have to understand what is the right observable for 4-dimensional gravity, because the S matrix of 4-dimensional gravity has these IR problems, but there has been some very interesting papers by various people recently trying to define an IR well-defined S matrix for gravity. And then the task would be to try to understand what principles this S matrix satisfies. Like, what is is it analytic? Is it crossing symmetric and all that? But those are very interesting questions, but we haven't really solved them or thought about them much yet. When you
The Reggie growth of what is the Reggie growth of the flat space graviton amplitude A of st over s squared going to 0 as s tends to infinity or whatever you wrote? What would that tell us about any putative holographic dual in flat space holography? If it was a CFT
oh
dual.
you mean the say if you're in 4-dimensional bulk and you're talking about a flat space
I
holograph.
suppose you don't have a 4-dimensional thing, but maybe you can say
Are you
D-dimensional.
asking about the CFT dual in the sense of usual holography, or in the sense of the flat space holography where the dimension is reduced by 2?
I'm thinking of the celestial holography business where you reduce dimension by 2, but maybe there's also something to be thought about the flat space limit of usual holography. Actually, maybe I can ask a better question. In ADS, if the Reggie growth is violated, then what gets violated in the CFT?
Well, so if eventually the Reggie growth must saturate. So eventually the amplitude is bounded because of the statement that the 4-point function on the second sheet is bounded by the 4-point function on the first sheet, and that follows from unitarity. So going to the second sheet is like going around the T-channel cut, and from the point of view of the T-channel, this only introduces some phases. So it cannot, it can only make the 4-point function smaller. So under the assumption of having an OPE with positive coefficients, which is always true in unitary CFTs, it cannot be violated.
Okay, so in some sense, it might be a violation of unitarity in the boundary CFT.
Right. And we probably don't like that. You would like that. That's a sacred principle that should not be violated.
Yeah, thanks. Have you thought about using these boost eigenstates and conform celestial amplitudes to put any new constraints on the betas?
Right. Yeah, that's an interesting point. We haven't, and it would be fascinating to try.
Cool.
We haven't thought about it.
Cool.
Okay, we'll stop the recording and then people can discuss as they wish for some time.